Well, good afternoon, everyone. So hopefully you got the email about Lab 3. It's postponed 1 week to April 11th. The reason is I took 2 lab periods to cover some of the tutorials, so I'm going to give you some extra time to get that done. Any questions about the lab? Any issues come up? No? Okay. Okay, so the next part of this course is going to shift in theme a bit. We're going to shift from some more applied concepts to some more mathematical concepts. This is a part of the course I introduced last year, and it's meant to be a similar kind of material you would have if you took Electrical 331 control theory, or if you took the controls course in mechanical engineering, but this is just an introduction. So it's about digital control theory. So my objective with this course is to turn it into a CyberPhysical Systems course, meaning that we want to design embedded systems that control the physical things in the world. And so examples of this would be like in a electric car, they have these voltage converters that convert from one voltage to another, and those are controlled. They have to be controlled at a very high rate by these control systems. Another example would be like a drone that's flying, that's being controlled in real time, or these 3D printers, or robots. Or my favorite example is these hoverboards, which are actually, you stand on them and it balances you, keeps you upright. My daughter has one of these, and it's kind of funny because it doesn't look like it's doing anything. It looks like it's being kind of controlled by the user until the battery dies and it spills her off instantly. So yeah, they're actively controlled. And that's the same kind of thing with this robot. This is an inverted pendulum robot that rides on 2 wheels, but it has this kind of inverted pendulum. It's got this structure where it's sort of this narrow piece of board, and it'll balance itself. I've always wanted to build one of these. I never had the opportunity to. But the idea is that this thing has a controller in it that constantly keeps it upright using the wheels. Otherwise, it would fall over. But control systems, as you probably imagine, they're everywhere. So like a self-driving car, obviously drives itself. Cameras control, the focusing system and the aperture. This is thermostat is a very simple type of controller, and then of course the drone. These are examples I showed from the first lecture. And so what is, if you were to define a control system, what it is it's made up of pieces. You've got a controller, which is normally a processor of some kind. So this would represent the NEOS 2 processors and any hardware that we design, in the special purpose hardware in the FPGA fabric would be a controller. And then you have something that you're wanting to control, which the terminology here is a little weird, but it's called a plant. The thing you're trying to control is a plant, and that comes from I think that term comes from manufacturing, the days of when you design these controllers to control an actual manufacturing plant. Sometimes it's called a process, but you generally you're going to have these 2 pieces, and then the plant has typically there will be sensors in it that sense certain things. It's meant to sense the state of the plant. So this would be for example, if it's a car, this could be like a GPS location or acceleration, that kind of stuff. Or maybe could be sonar sensors or radar, temperature, pressure, whatever it is you're trying to control. And so these are sensor readings that are sent back to the controller. And those sensor readings are called process variables. And then the controller acts on those, reads those process variables, and sends back manipulated variables, one or more manipulated variables that are used as input to the plant. So the plant outputs process variable and inputs manipulated variable, and the controller inputs the process variable and outputs the manipulated variable. So the manipulated variable is generally some sort of input to a controller or to an actuator. So this could be a valve setting or a robotic arm input or an accelerator for a car, something like that. So that would be the manipulated variable. And then the plant is generally also going to be subject to disturbances. So, there's going to be an external forces that act on this oftentimes that hopefully the controller is able to still correct for. So, and these disturbances typically are going to be read somehow through the process variables. So if this were a drone, for instance, that you were trying to fly, the disturbances would be like if there was a big gust of wind or someone grabbed it and tried to drag it down. And then the controller would be trying to keep it on course or at a specific altitude. So there's two different ways you can design a control system. The first is called open loop control. And so this would be like, for example, when you have something that you're trying to control, like a toaster, and you have a controller in there. And so in this case, your manipulated variable would be like cook time, how long you want to keep it in the toaster, or maybe the temperature, the cooking temperature, whatever the input is to that. And the value that you as a user, you want to have, you want your toast to be a certain brownness, right? And when the toaster gets done, it will produce toast with a certain color. And so the controller takes basically the color of the toast you want, and it sets the cook time, and hopefully you get the right color out, right? But it's open loop in the sense that the toaster controller, this controller, which is would be internal inside the toaster, it doesn't actually look at the toast color. It just simply takes the input from the user with the color, or usually it's like a 1 to 4, and then it adjusts the cook time, and then ideally it would be calibrated in some way where you can expect to get a certain color given a certain input in this controller, but there's no guarantees. And certainly this couldn't deal with any kind of disturbances in this case because, like if there's a power surge or something, right, or the voltage changes. And so clothes dryers kind of work the same way, basically. You say, I want the clothes dry, and then the controller in there sets the dryer time or the dryer temperature, and hopefully you get the dry clothes out, but sometimes it doesn't work because that's an open loop controller. Now that's to be differentiated from a closed loop controller, which is where you have a feedback that goes from the output of the process back to the controller. And so this way, like for example in a toaster, let's say, I've never seen a toaster that has this. It'd be cool if it did, but like let's say you had a toaster that had an optical sensor inside of it, and that the optical sensor could tell what the color of the toast was. And so when you tell it that you want brown toast, it would allow the controller to continually adjust the cook time or the cook temperature to get the toast to the color you want, and the controller would know the current color of the toast and would be able to adjust accordingly. And that way you'd be guaranteed, or assuming it's designed well enough, you would always get exactly the kind of toast color you want. So the difference is that this closed loop control is where you have a feedback signal back to the controller from the output. In this case, the output of interest, which is the toast color. Now you could have other outputs coming out of here as well. You could have internal sensors that would measure other things and also feedback. But as long as you have at least one variable feeding back to the controller, this would be a closed loop system, closed loop feedback control. Does it make sense? So this would obviously be a better design for a toaster in my opinion, but like I said, no one's made one yet. In this case, the controller would be considered the plant, and then you as a hardware designer would be designing the controller for it. Okay, so the first question is, how do you design control systems? Because you're trying to control physical objects, whether it be a robot or a car or a toaster, these are all physical processes. And as you probably know, physical processes are modeled with differential systems, differential equations. So that's generally the most common way that you can model both a plant and a controller is with a differential equations. Specifically, linear time invariant systems, LTIs, are probably the simplest way to do it. And so these describe systems of differential equations that are linear. And what that means is that well, I'll get to that in a second. As I mentioned, make sure I cover everything. In a system, each component is an LTI, and then the whole system as a whole can be modeled as an LTI with all the blocks in there that are interacting. Okay, so LTIs are linear, as I mentioned, and what that means is that it's an equation where you have state terms. State terms are variables, right? Now, state terms could be an input to a controller, any of the variables I talked about, the manipulated variables, the process variables. These are all variables, and they're typically represented, well, they can be represented as time domain. So these are time domain signals that are changing over time. And so, for example, you might have x of t, but since we're using these things to describe system dynamics, you can also have, for example, the derivative of f of x of t relative to t, right? Or the integral of x of t, right? So, or you can have the second derivative, the third derivative, or the second integral, third integral. Okay, so basically you just have what it is just, it's an equation with these state terms, and either you can have, each state term could be a variable or its derivative, one of its derivatives, or one of its integrals. Make sense? Okay. Now, as long as you can also have coefficients too. So, for example, you can have it's linear, so you can have coefficients. You can have like 2 times x of t plus 10 times the derivative of x of t minus 20 times the integral of x of t. And so you can take state terms. You can multiply them by coefficients, and then you can add them up or subtract them, right? But you can't multiply state terms by themselves. Like you can't multiply 2 state terms together, and because otherwise, if you did that, it would no longer be a linear system. So the idea is that you think of it like a linear equation, except in the equation, the variables are time domain state variables, or they're one of their derivatives or one of their integrals. Does that make sense? Okay. So that's what it means by linear. You can't have state terms multiplying one another or themselves. You can't have like x squared of t, for instance, and you can't have x of t times y of t. And then time invariant means that the coefficients aren't allowed to change over time. They have to be constants. Okay? So what that means is that an LTI will then have you can calculate the frequency response of an LTI, and you guys probably did this already in Electrical 222, I would imagine. So frequency response is when you put a signal in to an LTI. So obviously you have to associate, you would have to associate a variable with an input and another variable as an output, if you did that. So if you put an input signal in, the LTI can have an output that changes the phase or the amplitude, but not the frequency, right? So you can't change, the output frequencies will be the same as the input frequency, frequencies, but you can change. It changes just the amplitude and the phase, right? So if a system is if a system is linear in time invariant, then it's a LTI. Okay, so here's an example of one. So we have this variable u, and I don't even remember what these represent, but it doesn't matter. You've got u of t equals y of t plus dy of t over dt minus 6 integral of yt dt. Okay, so that's an LTI. It qualifies. Notice we have coefficients, constant coefficients, and everything else is just addition and subtraction in there. So this would describe these signals y and u. And now normally, as you probably expect, you would not deal with this equation in the time domain. You can switch it over to the Laplace domain, the S domain. And that turns out that's really nice because it's really simple. Basically, wherever you have first of all, the t becomes an S because this becomes a frequency domain equation. And then the variables are usually lowercase in the time domain, and then they're uppercase in the frequency domain. But the real nice thing about this is if you have a derivative, the derivative just gets translated into, the first derivative is just translated into S. You multiply by S. And if it's the second derivative, it would be S squared. Third derivative is S to the third power, right? Multiplied by the variable, right? And then if you have an integral, it's first integral is S to the minus first power. Second derivative is S to the minus second power, and so on, right? You guys had that, and you learned about that already, right? 222. Okay. So that makes it really convenient to represent differential equations by putting them in the S domain. Okay, so now I mentioned this idea of inputs and outputs, though, right? Because this is just an equation. So when you conceptualize a variable as an input and another variable as an output, now in this case, we're assuming that these are single input, single output. You can extend this to multiple input, multiple output, MIMO systems, but in this, we're not going to do that in this course. We're going to keep it simple. These are all single input, single output systems. So if you write the equation in a way where the outputs, all of the output variables are in are the numerator, and the output or the input variables are in the denominator. So if you write it, if you express it as y of s over u of s, right? Then this becomes a transfer function where y is the output and u is the input. Does it make sense? So in order to do this, you basically just have to use a little algebra. You're basically just taking these equations and just kind of rearranging them to match this structure. Does that make sense? So for example, in order to do that here, so this equation just describes the dynamics between u and y, right? But if I want to structure this where y is the output and u is the input, then I want to format this as a transfer function. And the transfer function, I just have to solve for y of s over u of s. Okay, so basically the idea is we want to take all the y of s's out and put them on one side of the equation, and and also the u of s's, put them over. And then what you're left with on the right-hand side, so the left-hand side is supposed to be y of s over u of s. But then that's the left-hand side. The right-hand side of the equation is going to be a polynomial of just s's. S values. Or it could be a ratio of two polynomials. You guys with me? Right? So the idea is that if you take this, so the first thing, we start with the time domain, we convert to the frequency domain, and then on the right-hand side of this equation, it actually is, this one's pretty simple because we already have u on one side and y is on the other side, and we can factor out y of s. So if you factor out y of s, it's u of s equals y of s times 1 plus s minus 6s to the minus first power. You see that? So I just factored out y of s, and then of course you divide both sides by y of s, and you end up with the transfer function y of s over u of s is 1 over 1 plus s minus 6s to the minus first power. So that's your transfer function. So that's starting with this and converting it down to this transfer function format. Make sense? And again, now you could also redo it and make u the output and y the input. Actually, you just have to, invert the numerator to denominator. But in this case, the way it's structured, y is the output and u is the input. Okay, so now this is something that actually surprised me a little bit when I first learned about this. You guys might already know this from 222. But an LTI can be stable or unstable, which means that a stable system will give finite outputs for any finite inputs at any frequency, right? Now what it means is that, like, if you have an LTI, there's a possibility, if you have an unstable LTI, there could be, for instance, an input that you can give it that's finite, just a regular old, signal, but at a certain frequency, it causes the LTI to blow up, to just grow like just have unbounded outputs, like diverge, right? Does that make sense? So generally, like in a physical system, this would be, for instance, like, if you have a, I don't know if any of you have done this, but if you have a spring, like if you hold a spring out, and if you go like this with it, if you go fast enough, the spring kind of doesn't move at all, right? And if you go slow up and down, the spring can, the bottom of the other end, like if you hold one end of the spring, you're looking at the other end, and you go slow up and down, the spring will kind of move a little bit more. But there's a certain frequency that you can hit where the spring will just keep going longer and longer and longer and longer, forever. Like that's when you hit its resonant frequency, and that's an example of how an unstable system can kind of explode, right? So a lot of physical systems are like that. By themselves, they're unstable. So if you just have a physical system with an input, and you give it and you manipulate the input in a certain way, it could cause the thing to go out of control. So an example of that is the F-16 fighter jet. Believe it or not, the way it's designed, the control systems on it are the airframe actually is inherently unstable. So if you were just controlling it directly, like if the pilot was directly controlling the F-16 fighter, it would be very easy to control it in a way that would basically put it out of control, and so as a result, they have to have a control system incorporated in there that when combined with the physical airframe and the physical control systems of the F-16, it makes it stable, which means that some of the controls that the pilot would put in have to be overridden and changed in a certain way before they actually go out to the control surfaces in order to avoid it from this uncontrollable behavior. And so the idea there is that if you have an unstable system by itself, if you combine it with a feedback control system with a controller, together, when you model these together, the whole system becomes stable, right? So one of the objectives of controllers, is to make an unstable system stable, right? That's one of the common things that you're trying to do when you're designing a control system. The other thing you're trying to do is generally trying to make the system reach a set point that is given by an external user, right? So you want to force it into a specific set point, but you also want to make it, if it's unstable, you want to make the whole system together stable. And that's the nice thing about these S-domain transfer functions, because if you model the plant, the thing you're trying to control, which in this example is the F-16 airframe and control surfaces, if you model that as an S-domain transfer function, and you model the controller as an S-domain transfer function, then you can then create a new model of the controller feeding the open loop control. You can just model that by just multiplying the two transfer functions together, right, in the S domain. Now that's the open loop control. The closed loop control requires a little bit more tweaking to get that, but basically by representing things as these LTI transfer functions, it makes it easy to take pieces, including plants and controllers, and kind of connect them together like Legos. Just piece them together, like take blocks and create this block diagram. And oftentimes, like, you'll have like a plant and a controller together, but this itself will then be controlled by a larger feedback controller. So you can also have these nested controllers nested inside of each other, right? But in this case, this is just showing, in this case, we just have one controller, one plant. You guys with me? Does it make sense? Okay, so the first question is, how do you know if a system is unstable? So, generally, what you're going to get is you're going to get a transfer function like this that's in the S domain. And the question is it stable or unstable? Well, how do you know? Okay, well, there's three ways that I know of. There's probably more. One way is to use an impulse response. An impulse is a signal that is zero everywhere except at time zero. So basically at time zero, you give it a finite output value, but that value is infinitely small and centered at time zero, and everywhere else is zero. This is called the Dirac delta function. It's just basically a very fast pulse that basically zero, pulse, then zero again. Now you might say, well, what's the point of that? So the reason why you use that impulse, you use it as an input. So you have a transfer function, and you use it as an input to your transfer function, and you see what it does. You see what the transfer function does, right? The reason why it's nice to use that is because there's two reasons. The first is that in the impulse, the impulse contains an infinite number of frequencies. So in order to create an impulse using sinusoids, you'd have to add an infinite number of them together. So it basically is a signal that contains every possible frequency. But the other nice thing about that is mathematically, the impulse in the S domain is a 1, is literally just the number 1. And so, as I mentioned, if you have an LTI feeding another LTI, you can multiply them together. Well, if the first LTI that's feeding the second one is a delta, is an impulse, then that LTI transfer function is just 1. So you just multiply 1 times the second. So in other words, walk back here a second. So if this system is a transfer function, and say this controller is let's say this is just an impulse. Let's say you don't have the feedback. You're just saying 1 feeds this. And so what that means is that if you just look at the plain transfer function, that is the impulse response. In other words, you get it for free. You literally just take the transfer function, and if you can convert it from the S domain back to the time domain, which is a big if, that can be a challenge. But if you can take the transfer function and bring it back into the time domain, then all you have to do is sweep time, and you see if it blows up or not. So you get it for free. You guys with me? Right, so the transfer function, just a bare transfer function, is actually represents the impulse response. Now you can also feed in a step response, which is a step, which is where you go from 0 to some constant in an infinitely small amount of time, like a binary signal, sort of, like as it transitions from 0 to 1, but it does it instantly. That's a step response. And that works too, because that type of square wave also is an infinite number of sinusoids added together. It contains all the frequencies. But that has its own, its S-domain representation is, I don't remember. It has a more complex, it's not 1, it's like 1 over S or something like that. So it's easier to use the impulse response. Everyone with me? Does that make sense? Okay, so that's, and I'll talk about how to do the inverse Fourier transform here Laplace transform here in a second. But the second option here is, if you take the transfer function, and this is actually an easier approach, if you look for the roots of the polynomial that's in the denominator, in other words, you look for the values of s that would create a divide by 0 here in the transfer function. Those are called poles. And if you look at the real portion of the poles, now by the way, the S, I didn't say this, but S is a complex. In the frequency domain, this is a complex number. Now, in this class, we're not going to be dealing with any transfer functions that have that actually have any imaginary part. So all the S values that we're going to look at are going to just have a real component. But if you look at if the roots of the denominator if any of the roots have a real component that's less than 0, let me rephrase that. If all of the poles have S values with a real component that is less than 0, that are negative, then the system is stable. Okay, so that's what they often call, if the poles are in the left-hand plane of a plot, where you think of in a complex plot where the horizontal axis is the real part and the vertical axis is the imaginary part, as long as all the poles are in the left-hand part of that plot, then the transfer function is stable. That doesn't include 0, though. 0 is no good. They can't be 0. But as long as all the real components of the S's that create a divide by 0 here, as long as they're all negative, then the system is stable. So that's actually a simpler way to determine if this system is stable. Does that make sense? Okay. So again, those are called the poles. Okay, that's the option 2. And option 3 is you can simulate the system. You can take the system and you can put it in MATLAB. And then you can actually provide an input to it, step, impulse, chirp, whatever, into the system and simulate it and see what it does, which is kind of like a computer simulation, right? But we're not going to do that. We're just going to look at in this class, we're just going to look at the poles of the transfer function. Okay, so this is what I already mentioned. So this is this Dirac delta, which is just a fancy word for an impulse. The impulse, it obviously, it's bounded. So the impulse magnitude is, obviously it has to be finite. Generally it's 1, right? But it's 1 for just at 0, and everywhere else it's 0, right? Does it make sense? So if x is, less than, yeah. So the impulse contains all the frequencies, and then of course I mentioned there's a step function which is similar to that as well. But we'll just use the impulse. Okay, so here's an example. Oh, so this is option one on the previous slide was, how does that work? How do you derive this notion that as long as the poles are negative or have a negative real portion, then the system is stable? Well, let's take an example here. This is the one I had. I think that's the one I had earlier. So the transfer function here is 1 over 1 plus s minus 6x to the minus first power. That was the example I had before. In order to find the poles, we have to find the roots of the denominator, right? So how do we do that? Well, we got to get it into a form where we can find the roots. So the way I would do it is multiply the denominator and the numerator by s. Okay, so that makes it s over s plus s squared minus 6. And then just rearrange it so we have s over s squared plus s minus 6. And then we can take the denominator here and rewrite it as s plus 3 times s minus 2. And so the poles here would be, there's two poles. And obviously there's a second order polynomial there in the denominator, so there's two poles. Well, up to two poles, I should say. And so in this case, it's s equals minus 3 and s equals 2. So either one of those values of s will make the denominator 0. So if you look at the plot, so this is the pole plot, where you have the imaginary and the real part. Real is horizontal. Then there's your two poles, right? Now, one of the poles has a negative real component. It's in the left-hand plane, but the other pole has a positive real component. So this is an unstable transfer function. So now the problem here, though, is how would we convert this back to time domain from S domain? That's tricky. Did you guys learn how to do that in 222? You do any of those?
I
don't remember. Okay. Well, I'm going to make it easy in this class. So generally, what you do there is you look at a table. So if you look at a table of Laplace transforms and inverse transforms, the table it's really common. These Laplace tables are all over the place. They have these, but there's really just one entry of the table that I look at here is e to the at, e raised to the at power. It's a nice little exponential, is equivalent to 1 over s minus a. If you do this is the Laplace transform, and then the inverse Laplace transform, of course, is if you have 1 over s minus a, you can go back to e to the at. Okay? So the question is, if we can express this equation in terms of 1 over s minus a, then we can just use this thing here, this e to the at, right? This inverse Laplace. The problem is that obviously this doesn't match that. I mean, this is 1 over s. First of all, this is a 1 over s minus a. It's like a constant over. Think of that as like a first degree polynomial, right? S minus a. So we got to get this into that form, or this as a sum of those, right? Is the idea. So we have to break that up into. We have to take s over s plus 3 times s minus 2 and break it into two pieces where we have a over s plus 3 plus b over s minus 2, right? And then you can then just go directly from these two terms to this, right? Because then, obviously this 3 would represent negative a, right? And then the numerator, whatever a is, would just be, a constant that you'd multiply. You'd bring that out and multiply it by e to the at. You guys with me? That make sense? Okay, so how do you do that? Anyone remember how to do that? Yes?
What you do is you multiply a by s minus 2 over s minus 2, and you multiply b over s plus 3 over s plus 3. You basically multiply each one by 1, put the factors there, then what you do is then you basically just cancel out the denominator, so you just get S equals A times whatever, A times S minus 2 plus B times S minus 3, S plus 3, and then you solve for each coefficient, basically.
Yeah, that's right. But I think that only works if, I think that'll only work if the, these two things are unique, S plus 3. I don't think it works if you have S plus 3 and S plus 3. But anyway, they're different. So in this case, we can apply that method. So you, the idea is that, yeah, like he said, you want a common denominator. So you take the A and you multiply that by S minus 2, and you multiply the B by S plus 3. And then that gives you a denominator of S plus 3. In other words, you basically multiply S minus 2 over S minus 2 times this side, and S plus 3 over S plus 3 times that side. And so you end up with the numerator like this, and the denominator is S plus 3 times S minus 2, right? And so now you have this equation, right? That looks pretty good, right? Except the problem with this is that you've got A and B, you have two unknowns and one equation. You can't solve that if you have two unknowns and one equation, right? You need two equations if you have two unknowns, right? Well, well, okay, let's just multiply both sides of the equation by the denominator, so that will eliminate the two common denominators on each side. So you have S equals A times S minus 2 plus B times S plus 3, right? And then you can do this trick. It doesn't always work, because you still have two unknowns in one equation. But if you set B to, like, you assume for the moment that S is 2, then you'll have 2 minus 2 here, and so you'll have A times 0, so it'll eliminate the A, right? And then B, the other side will be S plus 3 is 2 plus 3 is 5, so you have 5B, right? And then, of course, the S we said was 2, so you'll end up with one equation with one unknown, B. You guys with me? So you just basically set S to be, or actually what I should say is, you look at the case where S is 2, and so that eliminates the A, and you just end up with B, right? And then you do the same thing for the A side. You set B to be -3, and so that will eliminate the B side. -3 plus 3, 0, and that zeroes out the, multiply B by 0. And then on this side, you've got A is -3 minus 2 equals S, which is -3. And so that way you can solve, you end up with two separate equations where you're left with just B being an unknown in one equation and A being an unknown in the other one, right? And then you can solve for A and B. Okay, so if you do that, you end up with A is 3/5 and B is 2/5. And so now you substitute those back into here, and now we have two terms, 3/5 over S plus 3 plus 2/5 over S minus 2. And you can then do the inverse Laplace transform on each of these two terms separately. And so you end up with, this one was 3/5 is 0.6, and 2/5 is 1/4, right? So if you do the inverse Laplace on there, you go back to this table, and if you look at the table, it's 1 over S minus A is, the inverse Laplace of that is E raised to the AT. So you've got E raised to the -3t, because A is -3 for here, and A is 2 there. So you got -3 and 2, and then you have these scalars in front of them, so 0.6 and 0.4. Does that make sense? These are called the eigenfunctions of that transfer function. And then if you now you're back in the time domain. So then if you look at this function, obviously you could tell from looking at it, but if you plot it out, you can see that it's unbounded, right? It just goes to infinity as you increase time, right? Okay, so here's another. Now that's kind of a little bit hard to. So basically, let me back up here again. So what that means is that if this was a transfer function of a physical system, and you put an impulse into it, it would blow up, right? But it's kind of hard to imagine that happening in real life. So this is another. I think this is a little bit easier to understand. So I took the same transfer function here, and I put it into MATLAB, into Simulink in MATLAB, because in Simulink you can simulate these transfer functions. And so I took the step in this case, which is not the impulse, but the step. And as I mentioned, the step function is equivalent to the impulse in the sense that it has all the frequencies in it. So the step function, in this case, I had it step from at time 1, at 1 second, it goes from 0 to 1, and then it stays at 1. So just a square wave, and you put it in there, and you can see what MATLAB gives you. You get this kind of oscillating that kind of builds and builds, and eventually, continues to build up the amplitude. You see that? I tried this other thing too, where it turns out that those poles, so our poles are -3 and 2, right? You can put a frequency in matching those poles, but instead of hertz for the frequency, you have to use radians per second, which is just equivalent to, it's just another unit for frequency. So radians per second means that in let's see, how's that work? 2 radians per, this is what the sine wave looks like at 2 radians per second. So you can see that this thing, completes like about, so this is one cycle at 3.14. But anyway, 2 radians per second, this is what MATLAB generates for that. And that 2 radians per second matches up to that pole, that S equals 2 pole. Because if you put that input in, and again you simulate it with that sine wave, it does the same thing as it did with the, not exactly the same, but it has the same kind of behavior as the step function, where it kind of just oscillates with ever increasing amplitude. It's even worse there, though. See that? Okay, so how about a system that's stable? What would that look like? Well, basically, it would be easy to. It's easy to figure out, right? You can create your own transfer function. Just make sure that the poles are all negative, have negative real components, which in this case, like I said, we don't have any imaginary components. So just change the sign from that 2. That 2 had a sign. It was S minus 2. Just change it to plus 2, right? So just change the sign of that guy to create our own made-up transfer function, basically. And so this gives you poles at -3 and -2, which are in the left-hand plane, meaning that they're, the real values are negative, right? And then what you end up there is that you generate this as the impulse response, and you can generate the impulse response by calculating the eigenfunctions, which, just to quickly run through that. If you solve it the same way we did before, you end up with, when you do the inverse Laplace transform, it's 3 over s plus 3 plus -2 over s plus 2. So you convert this to the eigenfunctions, which is 3 times e to the -3t minus 2e to the -2t, and you then sweep your time variable, and you can see it starts out as 1, it comes down here a little bit below 0, and then it kind of pops back up, and then it stabilizes right here. So you have a minima here, but it's bounded, right? So that's the impulse response for that guy, and so it's stable. It doesn't blow up. Now here's the same MATLAB simulation. In this case, I took the same transfer function and I gave it a step input, and check it out. It responded pretty well to that step input. It kind of bucks up here, and then it just settles down and converges there on 0. So that's what you want to see, well, for a stable system. Any questions about that? Okay. Here's another simulation, in this case with a sinusoid shoved into it. And kind of interesting, I put in 2 radians per second as the frequency. You know, the amplitude is 1. And so we get the same frequency out, but the amplitude changes. So this ends up creating a filter that actually, whatever, it takes this frequency and attenuates it. So look, because the input amplitude was 1, the output amplitude is only 0.2. So this creates a filter. Okay, all right, so I mentioned this before. Transfer functions are in this form where they're basically a ratio of the output over the input in S domain. Okay, and the nice thing is that you can compose these things by essentially, you know, if you want to feed one system into another. Now the notation gets a little weird, but like, see, in this case we have, I've got this block labeled Y. It's kind of hard to see with the contrast. This one's Y, this one's G, and so this is Y of S. It generates a signal Y of S over U of S, which is the input, right? And then this guy is G of S, which is the output. Y of S is the input. So what I'm trying to say here is that the boxes are usually labeled with whatever their output is, right? So Y and G, and then the input is implied to be whatever feeding them, right? But you know, so this is like saying Y of S over U of S times Y of S over, or Y times G of S over Y of S, which is this. Y of S gets canceled out, so you end up with just G of S over U of S, right? Although usually they don't show. Usually the diagrams are simplified, but the point is that you just multiply these guys when you have an open loop style system where you've got one feeding another. Make sense? Okay, so so now let's do a quick example here, physical model. So like, let's look at an example. I talked about, you know, you can have springs, or obviously can be modeled with very simple differential equations. How about something even, obviously RLC circuits, which is what you guys already did, I guess, in 222, I would imagine, right? You can model RLC circuits with those. But how about just a simple physical system where, let's say you have a coin and you just want to push the coin to a specific location with your finger, right? Now that might seem overly trivial, but you can model this. So you have this, Y is the distance you want to move a coin. And U is the force that you want to apply, pushing that coin either forward or back, right? And so you'll often see, like, you can take that and conceptualize it mathematically by saying that you have U, which is the force, you're pushing it, and then you have to subtract from that force. There's a counterforce when you push something across the surface. That's the friction, right? And the friction is it's going to take out B, which is the coefficient of friction. But friction is scaled according to the speed that you're moving across it. So if you take y, remember y is the position, y dot, this is a notation that just means the first derivative of y, the position. The first derivative of the position is the velocity, so you multiply that by the coefficient of friction. So then that gets subtracted from the force that you're pushing into the coin, right? So that's the friction, negating part of the forward force. And then that's going to equal the mass of the coin multiplied by the second derivative of y, the acceleration, right? So this is the mass times acceleration. So this is the force that is effectively being applied after you take the force that you're putting in and you take out the friction. You guys make sense? Okay, so you can convert this to S domain. Now, in this case, I'm trying to use some shorthand just to kind of show you how these are generally written. Obviously, this first equation is time domain, but you don't have of t. You don't have t in there. They just take it out. And instead of showing derivatives like d of y over d of t, they just put the dot. That's what those dot notation is. So this is just a simplified shorthand, differential equation. And then if you convert it to S domain, you basically just take the y and make it capital. You get rid of the dots and you replace those dots with s and s squared, right? Because remember, the first derivative is s and the second derivative is s squared. And then you want to calculate a transfer function for this. So you got to get it into a form that's a transfer function form, where in this case you want to calculate, what are you trying to calculate? What's the output of this system? The output is the position of the coin, and the input is the force that you put in. So we have to get it y over u. Now notice again, I don't have y of s, I don't have u of s. I took that out. That's just, it is y of s, u of s, but that's the shorthand. It's just capital Y, capital U. Okay, so the first thing I do here is I factor out y. Well, first of all, I take this, I take this y, the second term of the left-hand side, and I add it to put on the other side. So we have u equals ms squared times y plus bsy. Then I factor out y on the right-hand side. And then I obviously divide both sides by y, so I get u of y equals that. But I don't want u of y. U over y. I don't want u over y. I want y over u. So you can just, again, you can invert both sides. So what you end up with is y over u is 1 over ms squared plus bs. Does that make sense? Now you might say, well, what's all these other variables? Well, obviously m is the mass. You can substitute in whatever the mass the coin is in there. And b is the coefficient of friction. So those are parameters for the specific situation you're in. Okay, so so the goal is to get this guy into a polynomial form, but you also want to have it to where you don't have a coefficient on the leading term, the s squared. So you can fix that pretty easily just by dividing everything by m. And then you also want to get it into a form where you factor the denominator, so you can look for the poles and the poles. And so you can then factor out s. So you end up with 1 over mass divided by s times s plus friction over mass, right? And so you can see there that the this is a second order system. You've got poles at 0, s equals 0, and you got a pole at s equals b over negative b over m, right? So this is actually an unstable system, believe it or not, because 0. Remember 0. If you've got a pole on the 0 line, horizontal, axis at 0, that's unstable. And they might say, wait a second, are you telling me that just pushing a coin is an unstable system? Yeah, it is unstable because, you know, obviously, well, I don't know actually how you make that blow up, but it's technically it's unstable. Okay, so yeah, so just to check that, I put it into MATLAB and simulated it. Yes.
So is the point that you're making that pushing the coin, it's something along the lines of friction gets lower as it speeds up, so it keeps speeding up. So theoretically, in that minimalized system, you could accelerate it forever. Is that the idea?
Could be, but it's usually the friction gets higher the faster it's going, I think, right? Yeah, you get more, it's minus BS. So yeah, y, as the speed gets higher, you get more pushback. So I don't know. It's a good question. I don't know exactly how that works out, but I simulated it in MATLAB using the step. And so again, this step, the idea here is that I go from 0 force to a force of 1 and keep it at 1, but that increase happened instantly, right? And when that happened, the coin went zew. I don't know, like, you know, I guess it would be, you know, I guess the idea is that it's this really fast, you know, increase in force. But yeah, I mean, it checked out, at least in the simulation. I don't know if I could reproduce this somehow, physically. Okay, so that's, yeah, the point there is that, you know, this, you can have this, you come up with these transfer functions and you create an open loop system by just multiplying them, right? Now the question is, how do you create a closed loop system, or how do you compute the frequency response of a closed loop system? I mean the transfer function. Okay, so we have this closed loop system. So, like for example, let's say we want to design a robot that pushes that coin. That's the objective here, right? We want to design a computer that determines how hard to push the coin to get it to where we want it to go, right? To a set point. How do we do that? Well, we create, I think we could create an open loop or a closed loop system. So let's create a closed loop system in this case. So we assume that the computer that's controlling it knows the position, because that's the input. And we know what we want the position to be, and we can determine what the force is. So the force that we're putting on the coin is a manipulated variable, and the position of the coin is a process variable. Okay, and then, so this is the plant, is the coin, this is the controller. So G sub C is the controller, G sub P is the plant. Manipulated variable is this G sub CS, which is going to end up being U actually, and then this is Y. Y is our output from the plant. That's where the plant's at. That's the process variable. But in this case, because it's a closed loop system, we also introduce this thing called rref, and this is the set point. This is where we want the coin to be. So this is like saying, like, okay, you want the robot to move the coin, you know, I don't know, 10 centimeters or something, right? So that's the set point. And so we take where the coin is, the position Y, and we subtract that from the set point, which creates an error, and the error is what we feed in as the input to the controller. Does that make sense? Okay, so, and you might have seen something similar to this in 274 when you took robotics. Okay, so you've got this, now the notation here gets a little strange. You've got this closed loop Y. So Y is, and this is where things are a little strange, because first of all, what's Y? y is going to be the output of this guy right here. This is y. This is the output of the plant is y. So the closed loop response of y is really just these three transfer functions multiplied by each other. So it's GP, GC multiplied by GP multiplied by this transfer function, which is just, this guy is RREF minus YCL. You guys with me? Now the reason that this is a little weird, because keep in mind this is Y. This line is Y, right? The names of the controllers are, the names of the transfer functions are GC times GP multiplied by this difference between RF and Y, okay? Now it seems simple, but again, we're relying on the fact that these S-domain transfer functions can just be multiplied together. Okay, so we could take this and multiply it out. So you've got GP, GC times RF minus GP times GC YCL. CL is closed loop Y. And then we can take this term and move it over to the left-hand side. So YCL plus GP times GC times YCL equals GP times GC times RF. And then we can factor out YCL, and that's then multiplied by, we've got YCL times 1 plus GP times GC. And then we can get YCL is GP times GC RF divided by 1 over GP times GC. So this gives us the transfer function expressed as the closed loop transfer function. Okay, so the problem is that this is fine, except the problem is that we need to know, so our input to the system is our ref. And so what we really want to know when analyzing this is this whole thing going to be stable where Y is the output and the input is our ref? That makes sense? So in other words, I just need to rewrite this. So what I need is YCL over RF. Because I don't have RF over here. I mean, basically, I don't have RF in the denominator on the left-hand side. That's the problem. So the idea is that once I build this, I can simulate this system by taking RF and going like this and trying different set points and making sure that the system still functions regardless of what I put in as my set point. In other words, I could tell the robot, move the coin, go 10 centimeters up, 10 centimeters down, and I can do that at any frequency, and I want to know if the system is stable. And also I want to be able to simulate that system as well. Make sense? Okay, so just a little bit more rewriting you got to do. So if you take, so you've got TCL equals YCL over RF, and so YCL is going to be, let's see, we're going to take, we're going to divide, yes, we're just going to divide, so we already have YCL here, right? And we're dividing the RF out of this. So what you end up with is the GPC times GC over 1. So basically this without the RF is your TCL. You guys see that? That makes sense. So basically all I did was I divided this guy by RF. And then Yeah, and that's it. That's basically where I'm at. So what you end up with is this GP-GC, these two guys, this is your open loop transfer function between these two guys, right? And so all you have to do to convert it from open loop to closed loop is to say you got to take the open loop transfer function divided by 1 over the open loop transfer function, and that ends up being the closed loop transfer function. Does it make sense? So in other words, that's all you have to add to get the, to go from open loop to closed loop. Yes?
I'm sorry, what's TCL again?
TCL is the transfer function of the full closed loop with respect to RREF as an input. Make sense? So the idea is that we want to to take this whole system, and we want to know the transfer function of the position of the coin. I need to relabel this, but this is Y here. This is the output of the plant, right? So we want to know the position of the coin as an output, where the input is RREF, right? Which is the set point.
The deviation from where you want to be.
Well, no, that's actually E.
Okay.
That's the error. That's not the ref is where you want it to be, not the deviation.
You're transforming the error to calculate the next step.
Right. Yeah, exactly. Yeah.
Okay.
Yeah, so this transfer function incorporates the error term, right? So this way I can look at the whole system as being basically just position over reference. In other words, position over where I want it to be. And so where you want it to be can be anything. You're allowed to put any finite value in there at any frequency, and the system ideally would be stable. Now, by the way, not all systems are stable even with their controller. Sometimes they're stable within certain constraints. This is a simplistic view where I'm basically saying, if a system is totally stable, it's stable over any input, right? And that's what I'm trying to do here. But in reality, most systems are not stable over any input. I mean, you're not going to design this robot and you're probably not going to give it a super high, you're probably not going to change the RF at a very high frequency, right?
Yeah.
In fact, it may not even be possible to do that. But I'm just, in this case, I'm kind of just, yeah, exactly. Okay, that's all I've got.